All right, guys. I want to do one more problem with you in regards to the law of cosines with navigation. The law of sines assignment. I had some questions last period about number 7. Number 7. There's two ways of doing it. Okay, but the maybe more obvious way, if you're going kind of off your geometry background, may initially lead you to a triangle that you think does not exist because of the amount of degrees that get put into it. Because you're working from one triangle to a second triangle. Okay, I kind of give you the picture here. You're told in number 7 that you've got triangle. You get these two triangles, okay? And they tell you that this one here is isosceles, okay? I think they tell you maybe they tell you that that's 17 and that's 17, and then this side over here is 22. And I think they tell you maybe this angle down here, let's just say 30 degrees. I think that's the person that asked me about this last period. And what they did is they worked in that triangle on the right, the one that has 17, 22, and 30 in it, okay? Look at the ordering of parts there. The ordering of parts is in what orientation? Side-side angle. And that is the ambiguous case, is it not? So when you go and you solve for, because what they were trying to do, because I think they asked you a couple different angles here, but one of the main ones is they asked you for that angle there. So this person said, well, if I find this angle, I should be able to use supplementary angles to come up with that one. And if I have that one, because this being isosceles, I automatically have that one, right? They're the same. And that's great, that's fine. But if you were to go through and do this work right away with this triangle on the right, using the law of sines, which is what you need to do, you're going to find out that this angle right here is like approximately 40 degrees. So how big is this angle here? 140, right? So what would this one be? 140. Is that too much for this triangle? Absolutely. Okay. However, because this was side-side angle over here, 40 is not my only option. The supplement is my other option, right? So couldn't that be 140? Then this one would be, for some reason, not pretty stubborn. That one would be 40. And then that one be 40, and is that enough for allow this triangle to exist? Okay, so that's kind of the approach that you would want to take with that problem. Another way of doing it, which I think is a little bit quicker, ignore that. Can I say sine of 30 over 17 is equal to sine of x over 22? Will that automatically give me that angle A? Okay, now they do ask you to go a little bit further after that. They do want, I think, this angle right here. Okay, and it might be that full angle. I'm not sure which one it is. But once you find that one, you know this one, you know that one. Okay, you can do some more work over here. Once you know that one, you can find that one. Does that make sense? And then it gives you that one. So there's a lot of geometry that you used a couple years ago to help you kind of sift through that one. Two approaches. I'm going to make a video. So the last class, make a video for that question, showing the multiple approaches, and I'll send that out later today. But just if you're a person that knows I was struggling with 7, I wasn't getting the right answer, but I thought I was doing everything right, that's the reason. Okay, you won't see a question to where you've got to think about the ambiguous case like that on a test or a quiz. Okay, you will see an ambiguous case, but it'll be just a direct ambiguous case. It won't be it showing up as you're trying to solve for something else. So this question here says 2 fishing boats start from a port. One travels 15 nautical miles per hour on a bearing of 25 degrees, and the other one travels 18 nautical miles on a bearing of 18 nautical miles per hour on a bearing of 100 degrees. Assuming each maintains its course and its speed, how far apart will the fishing boats be after 2 hours? What's a nautical mile? A mile on water. Okay. A mile on water. Now, is it, so if I were out in the Atlantic Ocean and I traveled a mile on the water, is that exactly the same as if somebody was on the seafloor and they traveled a mile? They're not the same, right? It's not the same length, okay? A nautical mile is, traditionally, it's 1/60th of a degree of latitude. Okay, you guys know your latitudes are, right? Like the equator, that's a latitude, line of latitude, okay? And you've got a lot of those from North Pole to South Pole, right? Between any two of them, we divide them into 60 parts, okay? Then traveling 1/60 of those is what we refer to as a nautical mile. It equates to about 1.15 traditional miles. Does that make sense? Okay, so it's a little bit longer than a mile that we use on land. Okay, but it is used in seafaring and air travel. Okay, so pilots and stuff like that we still refer to nautical miles. Does anybody know what a nautical mile per hour, what another word for that is? Knot. Okay, K-N-O-T. Okay, I heard somebody say we're traveling at, in a movie or something, they're traveling at 200 knots or something like that. Okay, that's 200 nautical miles per hour. Okay, so it's pretty fast, right? Okay, it's more than 200 miles per hour. But I mean, that's, you know, airplanes can travel that easily. Okay, so whether that's important, I don't think that's not important in this question, but I think it's important for us to understand that when we see why do we have to have that adjective? It's because it's a different thing than normal traditional miles. So we leave this port. They both leave this port. And one heads in a 25-degree bearing. Now, there's no north, south, east, or west link to that, right? So we talked yesterday, if that's the case, then you always start north and you move clockwise. So they're trying to give you kind of this pathway for that boat. So that angle right there would be 25 degrees. Okay. The second boat leaves the exact same port, but they go on a bearing of 100 degrees. So again, going in the exact same clockwise rotation. That's about 100 degrees. They're trying to give this boat that path. Is that okay with everybody? Okay. This red one traveled at 15 nautical miles per hour, and we did this for 2 hours. How long would that red path be? 30 nautical miles. Okay. The blue one traveled at 18 nautical miles per hour for 2 hours. How long is that blue one? 36. Our tablet's really having some issues today. 36. All right. So can I then talk about finding this purple distance right there? Okay. I'm going to pull this triangle out. I'm just going to redraw a triangle so it's not as cluttered. But the distance that we're looking for would be that one. This would be 30. This would be the 36. Do we know what that angle right there would be? How big is it? 75 degrees. Okay. Quickest way to find that 75 is to know that this one traveled 100. Okay, the 36 one traveled a degree, or sorry, at a bearing of 100 degrees. The other one traveled 25 degrees, or bearing of 25 degrees. Subtract those, and I should get the 75 that's between them, right? Okay, if you remember, that's the protractor postulate from geometry. Okay, to find the angle between 2 degrees, just simply subtract it. Okay, or the angle between two rays, subtract their associated degrees. Another way of doing it is maybe some of you saw, well, if this is 100, then doesn't that angle right there have to be 10? And if this first quadrant is 90, and I've traced out 25, doesn't that make this have to be 65? 65 plus 10, that gives me 75, right? So you've got those options. And the protractor fascia, a little bit easier, a little bit quicker, but regardless, you should get 75. Is that a law of cosines question? Yeah. So now I can say d squared is equal to 30 squared plus 36 squared minus 2 times 30 times 36 cosine of 75. Just real quick, before we even start typing this in, what would you say would be like the maximum distance that could be between, that these two boats could have between them? Let's say one of them traveled true north and the other one traveled true south. Okay, so it has to be less than 66 degrees or 66 miles, doesn't it? Okay, that angle of 75 is less than 90. Okay, and it's obvious. It's also less than 180. If there was 180 degrees between these two paths, one would be going north, one would be going south, right? And then that's going to be the positioning of where they would be the furthest away from one another, the furthest distance away from one another, and that would be 66 miles. Okay, so my answer should be less than 66 miles, correct? Okay, if we go through and do the law of cosines, the reason I say that, the reason I ask that, is because I get a lot of people to go 30 squared plus 36 squared minus 2 times 30 times 36 cosine 75. Make sure I'm in the right mode. Good to go. They get that, and they answer with that. And they say 1636 is the distance between them. Well, that makes absolutely no sense, okay, based off the logic that we just said that it has to be less than 66 miles. So we need to square root that, right? Fastest way to square root the previous answer is just to take the square root of the previous answer, or raise it to the 0.5 power, and I get that. Okay, so 40.45. Is that right? Now that's nautical miles, right? Okay, nautical miles. And a nautical mile is about 1.15 miles. So if I multiply that by 1.15, actually about the miles that you are accustomed to is about 46 miles, 46 and a half miles. Does that make sense? Okay. Obviously, this question just asks you to leave it in nautical miles, so you don't have to do any of that unit conversion or anything like that, but that's kind of how you can see how those things relate. Is that something we can do? All right. I want to get into, so the law of cosines assignment is open until Monday. If you have any questions over there are some story problems towards the end of that. About half of it is just traditional. Here's a picture of a triangle, solve it. Okay, find the 6 parts of it. And then eventually in the second half, you start to see story problems. In those story problems, if you're struggling, bring that up to me. Okay, send me an email or something like that, and I can get you some feedback. I think those are important to be able to analyze and mess around with. Okay, we're not going to get too far today in Chapter 6. You guys might get a little bit further than what first period did. But I want to start introducing the unit circle, okay? So there were some things in Chapter 5 that we messed around with that maybe were problematic for some of you, okay? For instance, the questions that say rewrite sine so it's in terms of cosine, or rewrite tangent so it's in terms of secant, okay? Those things were maybe somewhat difficult because we're not used to that. Okay, we haven't seen a whole lot of stuff, but it's essentially just taking, like if I gave you the equation 2x plus y equals 13, and I told you to rewrite that in terms of y, you would say y equals negative 2x plus 13. okay? You would solve for that variable. The same kind of thing is happening trigonometrically. And the goal for us to learn, or the reason we're learning that stuff, is that in calculus we're going to be asked to solve some equations that have trigonometric ratios in them. And the process of solving those equations is very difficult if there are varying trig ratios. If I have an equation that has sine and cosine in it, that's hard to do, okay? Jacob asked me last class, he was working on this question from calculus. He had to take, and this will be a question we do here, it was an intermediate step in his calculus question, but he had sine squared x, I think it was maybe plus sine of x minus cosine squared of x equals 0. So basically what he's trying to do, that's a derivative. He's using derivatives to help him find where maximum minimums are on this previous curve, okay? So he finds this derivative, do that. Now he's got to find out where this derivative is equal to 0, and that will tell him the locations of his maximums and minimums. So he's got to solve that, okay? And if you look at that, it's sine squared plus sine x minus cosine squared. There's problems with that cosine squared there, right? We got two trig ratios, okay? Well, from section like 5354, we introduced this idea that sine squared x plus cosine squared x was equal to 1, right? So doesn't negative cosine squared x, just kind of jockeying these things around using my algebra skills, doesn't opposite cosine squared x equal sine squared x minus 1? Okay, so can I plug that in right here? Does that make sense to everybody? So now I've got sine squared x plus sine x, okay, plus sine squared x minus 1 equals 0. That's 2 sine squared x plus sine x minus 1 equals 0. Now this looks ugly, but let's do this. Let's let u equal sine x. So wouldn't u squared equal sine squared x? Doesn't that give me 2u plus u minus 1 equals 0? Oh, sorry, it's 2u squared. And is that something you can factor? Absolutely. Okay? So that is just trying to foreshadow something that we're going to be asked to do on a regular basis later on in this course, and then ultimately in calculus. It's just something that happens periodically throughout a series of questions that you just have to know how to do it, right? It's like now when something shows up where we've got factoring of a quadratic, we don't go back through and reteach that. We just know it's a skill we've developed, and we can use it whenever we need to. This is what we're trying to get to, all right? So in trying to get to that point of being able to solve things like this, we need to understand really what is going on with all this sine squared, sine x, cosine squared x, all that kind of stuff, and what it kind of means to us graphically first, okay? So that's kind of the end task. But as we're getting there, we're going to do individual problems that help us learn these concepts and understand these relationships a little bit better. But that's where we're going, okay? In doing that, we want to talk about the unit circle. Now, some of you who are in physics maybe talked about the unit circle when you were dealing with vectors. There's some other, maybe somebody was talking last class, you guys are doing angular velocity, circular motion, that kind of stuff. Probably using some unit circle stuff there, okay? I was told that maybe you're not all that familiar with the unit circle, okay? The unit circle is, let me see if I got a picture of this. Yeah. There's the unit circle, okay? It's just a graphic organizer of a bunch of angles in the unit circle, the circle that is got a radius of 1, okay, inside the Cartesian plane, and then points that exist on that circle in the Cartesian plane, okay. So you were probably in physics just shown the first quadrant, okay, from 0 to 90 degrees. Well, the circle centered at 0, 0 is symmetric about the x-axis, y-axis, right? So that's why you're probably only showing the first quadrant, because if you know the first quadrant, reflect it into the second, and now you know the second quadrant. You just got to change the signs. Once you know the first and second quadrant, reflect it in the third and fourth, and you change the signs accordingly, and you have the information in that fourth one, or third and fourth one. We'll get there. I'm going to teach you how to replicate that, how to produce that. It's very easy if you understand symmetry, and you can count to 2 by 6s. Okay? So 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 6, 8, 6, 9, 6, 10, 6, 6, 11, 6, 12, 6. You can all do that, right? And you can create the unit circle. Okay? What I need you to understand, unit refers to the number 1. Every time in mathematics you see them say unit circle, unit vectors, unit whatever, they're talking about 1, okay, or a length or magnitude of 1. So what is the only thing that dictates the size of a circle? The only dimension that dictates the size of the circle? The radius, okay? So in the unit circle, the radius is 1. Does that make sense? So what we're doing here, when I talk about the unit, and a lot of people lose sight of this, and things get really messy and confusing and just way out of line if we lose sight of this. When we're dealing with the unit circle, we are placing the origin of the circle, the center of the circle, on the origin of the x and y axes. Okay? Therefore, when I'm looking at the unit circle, I am zoomed in on that 2 by 2 square in the unit circle, from -1 to +1 on the x-axis, -1 to +1 on the y-axis. The circle that exists inside that block is, with a radius of 1 is that red circle. Does that make sense, everybody? Okay? That red circle is the unit circle. There are an infinite number of points on that circle, correct? Okay? If you remember from college algebra, every single circle we come across is of the form of that, right? You remember that? Okay? Where h and k are your center. Well, our center here is 0, 0. Okay? So h is 0, k is 0. So all I get is x squared plus y squared. And we said our radius was 1, right? Okay? Now, the reason we do this and we interpret this stuff with a radius of 1 is because if we can learn that, then what we have is a bunch of, no matter what circle I ever want to look at, whatever triangle I ever want to look at, kind of think about this. Let me get rid of this quadrilateral real quick. If I were to take, let's say, that ray right there, okay, and I create maybe that triangle right there. Does that make sense? Okay. I'm going to try to make this a right triangle. I don't know if that's a right angle right there, but let's view this as a right triangle. Okay. If I were then to have a circle that looked like maybe that big. So then I have maybe that triangle. What would you know about those two triangles that I just drew, the one in the unit circle and the one in the circle that has a radius of 3? They're similar, okay? Meaning that their sides are proportional, right? Okay? And if their sides are proportional, the things that we learn about that first small one is going to allow us to learn everything about that big blue one, okay? Which, if you, I don't remember what section it was that I asked you to look at in Chapter 5. There was some information about that. I try to explain stuff like that. So the idea is, why do we use the unit circle? Well, it makes things a little bit easier, okay? Than working in a circle that has a radius of 3, or a radius of 2, or a radius of 15.4, or whatever. It doesn't matter. The unit circle is easier to work with, okay? And what we can learn about that is going to allow us to take that information and pass it on to other circles and other triangles, okay? So that's kind of the breakdown of the unit circle. That's the kind of, I don't know, the explanation of what it is and where it is, okay? The next thing I want to do is kind of talk about some terminology that we've dealt with, okay? This point, G, is a point on the circle. Let's see if I can get its value up here. All right, so 0.74, comma 0.67, and it's obviously probably not going to be whole numbers, right? Okay, and obviously it's not going to be whole numbers because it can't be any bigger than 1 or negative 1, right? And for either x or y. But what this is because that point is on the unit circle, I should be able to take 0.7437, square it. Take 0.6685, square it. Add those two numbers together, and what should it give you? Think about that. Let's just try this, okay? Now, the way I can do this, I could say I want the x value of g. That's how I can write that. Does that make sense? So it's going to pull out this number. And I said I wanted to square that. Then I want to add to it. I want the y value of g. So it's going to pull out that number. And I want to square it. What should that equate to? Any ideas? It should equate to 1. And you see that it does. Okay? Any point that is on the unit circle, when I square the x and then square the y and then add those together, I get 1, right? That's any equation ever, right? The points that are on it, if I take that line right there, which is this equation, okay? If I take that point h, which point h is negative 2.6095, comma 1.9281, if I plug that information there of h, into that x and that y, what am I going to get back? Negative 3.8245, right? I'm trying to satisfy an equation. So that's what you know with linear equations. The same thing happens with circles, which are nonlinear equations. Okay? Now, where does the unit circle kind of, what's its use? Okay? And how does this relate to angles that we've been talking about? If I look at this initial point F and this, let's make a ray here. That terminal ray that goes through G, would you agree that there is some angle right there? Now, I don't want to show the labels here. That we get that green angle, right? That green angle is always associated, and we're going to talk a lot about this. That angle there is associated with that point G. Okay? It is also associated with this distance right here, that portion of your circumference. Does that make sense? Do you guys remember from geometry? If I were to find arc length, and this is also part of section 5.1, I think. If I want to find arc length, in geometry we talked about it as being the ratio that this was of the entire circle, right? Okay? Or the ratio that this angle was of the entire circle. So I'm going to take that angle, whatever it is, let's just call it x degrees, divide it by 360 degrees, and then I would multiply it by my circumference. Remember talking about that in geometry? We get 2 pi r here. That's my formula for circumference. So if I want to find that length of that blue segment, I would do that. Okay, and that's when I'm working in degrees. Now, here's a reason why working in radians makes much more sense than a lot of the things that we do. Okay, because if I was working in radians, okay, instead of calling that angle x, a lot of times we call it theta. Okay, and if it's in radians, what is one complete cycle around the circle in radians? 2 pi. So that would give me the ratio, the portion that this arc is of the entire circle, right? Okay. I mean, if that's like 45 degrees or pi over 4 radians, it would tell me essentially that that is 1/8 of the entire circle. Okay. Well, what happens with this 2 pi here and that 2 pi there? They cancel out. So now I get arc length to equal theta, which is your angle, times r. Is that formula a lot easier, a lot simpler than what we started with in degrees? So that's one of the benefits of working with radians, is because it makes things simpler. Okay. Now arc length. Does anybody remember the letter that is used to describe arc length? It is S. Okay. So we learn in chapter 5 that S equals theta R as long as theta is in radians. Here's my question to you. We're looking at that blue arc up there in the unit circle. So what is R? It's 1. So if R is 1, S is equal to theta. Does that make sense? S is the blue distance. As if you were to stand on F and walk to G along that arc, that is how long you would walk. That would be a distance. Well, they're saying here it is equal to theta. Theta being the green angle in radians. Okay? Has to be in radians. Okay? So, that's nice. Okay? That's a really, really good thing. So if I tell you that this angle right here is pi over 4 radians, then this distance right here, pi over 4. Okay? Now what happens is that in section 6.1, we start talking about that distance and being asked about that blue distance and that kind of thing. But I think, my personal belief is that working with that angle makes much more sense, I think. But if you understand this S equals theta, they're synonymous. It doesn't matter which one you're talking about. Now here's the thing. It happens, it's because of labeling and that kind of thing that in the past that people sometimes struggle with. They call that S equals theta in chapter 5. Arc length was S. Now what we're going to do in talking about that distance there, instead of using S, we're going to use T. Okay? Because point G is the terminal point for that blue arc. Does that make sense? So because of the terminal point, we use the letter T to abbreviate that. Okay? But it's referring to that distance around the unit circle. Does that make sense to everybody? Okay. My fear is to just start giving you the unit circle and telling you this is how we use it, this is what you do with it, and then if you pick up on that, great, but there's still going to be confusion because you're not sure why we're doing what we're doing. I think if you understand this link here, it's going to help a little bit. Let's see here. You're going to get questions like this. It says, show that point P, which is at radical 3 over 3, comma, radical 6 over 3, is on the unit circle. Okay? Well, we know the equation of the unit circle is x squared plus y squared equals 1. This is now an x value, and that is a y value, right? Should that satisfy this equation? Should I be able to take that x value and square it? Add to it that y value and square it. And what should I get? I should get 1, right? It says show. Basically, another way of saying show is prove. So you need to provide the work. Okay? So I fill this in. I'm asking, is this true? Well, what's radical 3 squared? 3. What is 3 squared? 9, right? So radical 3 over 3 squared is 3/9. What's radical 6 squared? 6. What's 3 squared? 9. Does 3/9 plus 6/9 equal 1? Yeah. Okay? You've proved it. You've shown it. Does that make sense? Okay? Now, let's see here. If I were to ask to find, what was it, the square root 3 over 3, comma, square root of 6 over 3. Is that point on the unit circle? Yeah. Okay. Now, here's something that I think is important. If we go back to the unit circle, there's a lot of things that are on that unit circle. There are values of, let's see here. See if I can do this easy. Let's get rid of these segments. Let's get rid of all of it. No, I don't want to do that. Why do the segments disappear when, or circles disappear when I do that? All right, D, E. Okay, we're going to start with F. So I'm going to say that F is just equal to the number 1/2. No, not 1/2. Let's go square root of 2 over 2. Let's say G, let that be 1/2. H equals square root of 3 over 2. Okay. What happens here, and I'm just doing this to make it easy, if I want to look at, like, let's say, the point radical 2 over 2, comma, radical 2 over 2. So this is radical 2 over 2 right here, right? I want to look at that point. I'm just going to type in F, comma, F. See how that point's on the unit circle? Okay. If I want to go H, comma, G, so that would be radical 3 over 2, comma, 1/2. Is that point on the unit circle? Okay. If I wanted to go H, comma, G, what did I do? H. Oh, I already did that one. G, comma, H. That one. On the unit circle, right? Okay. Now, if I put on, I don't know if I can do this. Let's go surd text H. Okay. There is H's ordered pair. Okay. Let's look at the angle that is associated with that. Z. 30 degrees. It's kind of a nice whole number degree, ain't it? Okay. Type in on your calculator sine of 30 degrees. I go sine of 30 degrees. It's going to be 0.5. Is there a 0.5 over here? Okay. Type in your calculator cosine of 30 degrees. .866. That number right there is 0.866. You kind of see that neat relationship that occurs here? Okay. If I look at the angle that goes to G, 45 degrees. So there's the ordered pair for 45 degrees. And it's the exact, it's not the decimal, right? It's radical 2 over 2, comma, radical 2 over 2. Okay? Type in sine of 45 degrees on your calculator. Now, radical 2 over 2 is 0.707, right? Sine of 45 gives me that. That number right there. If I typed in cosine of 45, it's going to give me that number right there. Does that make sense to everybody? Okay. You know, if I did 90 degrees it'd be this point right here. What's the ordered pair for that point right there, where my cursor is? What's the x value of that point? 0. What's the y value of that point? 1. Type in sine of 90 on your calculator. You get 1. What's the cosine of 90? You get 0. Okay? So what that's allowing us to do is to kind of pick off some real convenient angle measurements that we use a lot. 30, 45, 60, 90, okay? And then multiples of those to generate the ratios the sine, cosine, tangent ratios much quicker, okay, than using our calculator. The issue becomes, and this will be part of what we do, what if I want a 15-degree angle? Well, there's a 30 and a 45 that we know information about now, right? If I subtract those, can I get 15? All right, we'll talk about how do we mess around with the ordered pairs to get that 15-degree measurement. But all of this, so this is the relationship of the unit circle, but is that exactly the same thing as what we did in Chapter 5, or very similar to what we did in Chapter 5? If I zoom in on this, just to make it a little bit bigger for you, if this is the unit circle, is that length 1? If this is a right triangle, and where my cursor is a 45-degree angle, is that a 45, 45, 90 right triangle? Okay, if that's a 45, 45, 90 right triangle, this is n, and this is n radical 2, right? You just told me n radical 2, that side was equal to 1, right? Well, then n is equal to 1 over radical 2, which simplified is that, right? So it tells me that distance right there is radical 2 over 2. That distance right there is radical 2 over 2. Isn't that how I get to a point? I go on x distance, radical 2 over 2, and then I go on y distance, radical 2 over 2, and that should put me right there at G. And that ordered pair, radical 2 over 2, radical 2 over 2, puts me on the unit circle. Okay? So there's a link between the unit circle and our special right triangles, right? Okay? So if you remember back to geometry, I would always tell you, we're going to learn a lot about triangles because they tell us everything about every other shape, right? And then I'd say they even tell us a lot about circles. Okay? This tells us a lot about these triangles tell us a lot about the unit circle, and then the unit circle tells us a lot about other circles and other triangles. Okay? So that's kind of the plan as we move forward. It's going to be an efficiency thing. And with obviously you can grab your calculator, and if I say sine of 270 degrees, you can grab your calculator, type that in, okay? But efficiency-wise, when I say sine of 270, we should all instantly, within the next couple of weeks, automatically know that that's negative 1, okay? And that's the hope that's going to allow us, that we're going to develop that skill that's going to allow us to be very quick with our calculations. Nothing new in regards to homework tonight. Tomorrow we'll go through the rest of set 6-1, and